Chapter 3, Exercise 2, Part A, show that A cross B union C is equal to A cross B union A cross C. Part B is show that if A cross B is equal to A cross C and A is not the empty set, then B is equal to C. Right, this is a standard Enderton certified set equality proof, and we're going to solve it as we usually do. But before we do that, it's important, I think, to just clearly define what the cross product of two sets is. Now, A cross B for any two sets A and B is going to be the set of ordered pairs x comma y such that x is in A and y is in B. Right, we may have not come across this notation right here. This just means that instead of x comma y being a set, it is an ordered pair, meaning that it does matter where exactly each one of these two lies. I encourage you to read the formal definition of these ordered pairs. I'm not going to go into it. It's at the beginning of chapter 3. For now, all we need to know is that these elements have an order and the order matters. Okay, so let's get started. So let's suppose that x comma y is in A cross B union C. Then by definition we have that x is in A and use a fancy ampersand, and y is in B union C, right? Y is in B union C means that y is in B or y is in C or both. Right, if y is in B, then x comma y satisfies x being in A and y being in B. So x comma y is in A cross B, which just directly implies that x comma y is in A cross B union A cross C. Phenomenal. And then the reasoning for the other one is the exact same. So if, on the other hand, y is in C, then x comma y satisfies x is in A and y is in C. So x comma y is in A cross C, which implies that x comma y is going to be in A cross B union A cross C. Cool. If y is in B and y is in C, both cases apply. So x comma y is in A cross B union A cross C. Cool. Now this means that A cross B union C is a subset of A cross B union A cross C. And there you have it. Now let's do the backwards inclusion. Let me add a new page before I run out of space. Might need to add 2 more pages, so give me 1 second. There we go. Right, back to it. Now suppose x comma y is an A cross B union, or rather, I'm going to call it z because it's the element of a union. So z is in A cross B union A cross C. So z is in A cross B, or Z isn't A cross C, or both, as usual. Right, what does this mean? So Z is going to be equal to A comma B, where little a is in big A and little b is in big B, or Z is equal to A comma C, where little a is in big A and little c, oh my god, is in big C. There we go. This, of course, being whether this is real or this is real. So if Z is an A cross B, Z equals A comma B, where little a is in big A and little b is in big B. Now, big B is a subset of big B union big C, so little b is in big B union big C. So, A comma B, Z isn't A comma B, where A is in little a is in big A and little b is in B union C. Thus, Z is in A cross B union C. And then the reasoning for the other one is the exact same. If Z is in A cross C, then Z is equal to little a comma little c, where little a is in big A and little c is in big C. So, or rather, by the same line of reasoning, little c is in B union C. So Z is equal to A comma C, where A is in A and C is in B union C. So Z is in A cross B union C. Okay. Now if both apply, if Z is if Z isn't A cross B and Z isn't A cross C, then you can do, like, both of these cases apply. I can see how it's a little confusing at first, but the idea is that Z can be written in this form for both sets. So you can write it as A comma X, where X can be in in B or C, or then rather I'll just write it out. Then Z is equal to A comma X, where X is in B and X is in C. So X is in B intersects C, which implies that X is in B union C. So A comma X, or rather, I'm just saying Z is in A cross B union C. There you go. Same case, same rules apply. Yeah, the general idea is that I don't even know where I was going with that, but it's the exact same proof for all three cases. Right. This tells us that A cross B union C is equal to A cross B union A cross C. And there you have it. That's part A. Now part B is, well, I have it right here, is that A cross B equals to A cross C. I'll just write it out in a logical way, and A is not equal to 0, or empty set. This implies that B equals C. Okay, so this is an implication proof, so we assume the left-hand side, also known as the antecedent, and we prove the right-hand side is true, also known as a consequent. So assume A cross B is equal to A cross C, and A is not equal to the empty set. Okay. Right. So we're trying to show that B is equal to C. So let's do this. Suppose B, little b isn't big B. Then for all A and big A comma B is an A cross B. Right? Because B is in B, as we assumed. A is an A for any one of these you pick, so this has to be true. But A cross B is equal to A cross C by assumption. So A comma B is an A cross C. This implies that little a is in big A and little b is in big C. So little b is in big C. Thus, B is a subset of C. And then that is the general proof structure that we're going to use. Do the exact same thing, just swap around B and C. Now, suppose little c is in big C. Then for all A in big A comma C is an A cross C. But A cross C is equal to A cross B. So, A comma C has to be an A cross B. Thus, A is in A, C is in C is in B, sorry. Meaning that big C is a subset of big B. Thus, B has to be equal to C, since these two sets, as we've shown, are subsets of each other. And then it follows that, what were the assumptions we had? A cross B is equal to A cross C. And A not being equal to the empty set implies that B equals C. Right, and you may be wondering, well, where exactly did this assumption go? So here we made an assumption that for all A and A, right? Now if A is not the empty set, then this right here is the empty set, because as you might recall, A cross B is the set of AB such that A is in A and B is in B, right? But if there are no elements in A, then there are no such pairs of this form. So if A is equal to the empty set, implies that A cross B is also equal to the empty set, because there are no ordered pairs that satisfy any of this. So if we were to assume that this is that A is not the empty set, then we couldn't make this assumption, for instance, or we couldn't, first of all, we wouldn't be able to say that this is true, so we wouldn't be able to make these inferences, specifically this inference right here. This is where you can like bridge between B and C by their cross products being equal. Now note that if A is equal to the empty set, then A cross B is equal to the empty set, which is also equal to A cross C. So there's like some level of vacuity, and I think this is exactly the case that Enderton was shielding himself from when saying that A has to be different from the empty set. Right, hope that didn't confuse you too much, and I hope this was helpful. That is all for this exercise, and I will see you in the next video. Bye-bye.